Alrighty, good afternoon, everyone. Thanks for coming today. So today we're going to be talking about EV battery technology. So last time, remember, we were going through all the different components of the drivetrain. The one thing that I was kind of leaving out is the battery, which we'll focus on for the entirety of today. All right, so yeah, batteries, what are they and how do they work? Okay, and so there are lots of different types of batteries out there. I'm sure all of you guys are using these in even your everyday life. They can be structured in many different ways, but the basic components of batteries are going to be pretty much the same across the board. And so those major components are your cathode, your anode, and then having some kind of electrolyte, which is the medium that helps to conduct all of the electrical materials. So cathode is your positive terminal, anode is your negative terminal. You can remember positive and negative because there's a T in cathode that's kind of like a plus, right? And the way that a battery works is that there are sort of free-flowing ions that travel in the electrolyte. And as these travel, they can actually induce electrons to flow between the cathode and anode, which is what is actually generating electricity. So when you are charging a battery, typically you've got ions essentially kind of getting stored up on the anode. And then when you discharge, you are exchanging those ions through the electrolyte medium to the cathode and then inducing this kind of flow of electrons. So the energy that is being stored is the electrical potential difference between the anode and cathode. Because when you're charging up the battery, those ions actually really want to go back towards the cathode. And you can imagine that things that are more energy dense and more power dense, right? So if we compare, like a AA battery compared to like a car battery, right? The properties of these batteries might be a little bit different. The larger you have this sort of potential difference, essentially the more energy and power that you can get out of the battery. And so for some applications, you don't need a lot of energy and power density, and so that might be in the form of these sort of cheaper batteries. But then when we think about the application in something like a vehicle, that's where you're pushing these several thousand-pound vehicles around. You're going to need a lot more energy. And so it's actually taken a little bit of time for battery technologies to enable electric vehicles. So before we kind of talk about specific details of batteries in EVs, there's some nomenclature that we need to discuss. And I'll also talk a little bit about how batteries operate in general. So this nomenclature, this is kind of like the foundation for us to be able to talk about batteries. And so the first one is state of charge, or SOC. This is how much energy is left in the battery. You guys see this every day on your phone, right? You look at it and it's like, oh, it's 100% charge or it's 80% charge, right? That's what this is referring to. Essentially, as you use up the energy, your state of charge goes down. If it's fully charged, you'll be at 100%. Although I'm going to caveat that a little bit in just a second. The capacity dictates how much energy is stored in the battery when it's full, right? And so we've been talking in units of energy and power, and so capacity would be a description of energy. And so we usually talk about, in the vehicle side of things, units in terms of like kilowatt hours. Okay, effective or net capacity. So here's what I was mentioning with the sort of caveat with batteries. So it turns out that having a battery fully charged all the way to its like nominal capacity, so at 100%, or fully discharged all the way down to 0% is actually really bad for the battery. One of the things we'll talk about is battery degradation, which is a loss in sort of capacity over time. If you are fully charging the battery and fully discharging the battery, you will degrade your battery faster. You can think of this like on the anode and cathode, you're putting so much sort of pressure on the battery that it starts to essentially degrade, lose the ability to hold on to ions. And likewise, if it's all the way empty, it can be hard to get it start charging again. So what you guys actually see on your phones and on your laptops and even in vehicles, that like 0 to 100% isn't the full range of the battery, okay? And so if I had like 100 kilowatt hour battery in like a vehicle, it may have a buffer kind of at the top and at the bottom. And so your effective amount might only be like 90 kilowatt hours. And that's the same for your phones, right? So if you're charging to 100% on your phone, there's actually a little bit of buffer left at the top. And same if you discharge your phone all the way to 0%, there's a little buffer at the bottom. And so when we talk about net capacity, that's different from the nominal capacity, which is like the true amount. The net capacity is like what the manufacturer has unlocked as the usable range of your battery. So just know that you're not using the full battery, and that's actually a good thing. And actually, some phones, for example, like I know Apple does this, I don't know, I'm sure Android has these, Android phones have these options too, but you can say, like, oh, I don't want to fully charge my phone. I want to set it up to like 80% or 90%. And that's actually adding additional buffer. And we'll see how much of a difference that makes in just a moment. Okay, battery cycling or charge cycling. This is the process of discharging and then charging a battery. So when I talk about cycles, that means that I'm using the battery and then recharging it, and that counts as a cycle. And we think about the lifetime of batteries as being able to sustain some number of cycles, right? And so if I say, oh, like 10,000 battery cycles, that means I'm discharging the battery and then charging it up like 10,000 times. And then the depth of discharge is the amount that you would discharge in a particular cycle, right? And so if I have 50% depth of discharge, that means I'm going from 100% to 50%. If I'm doing an 80% depth of discharge, I'm going from 100% down to 20%. Yeah, and actually doesn't have to start at 100%, but the depth refers to the amount of your capacity that you're discharging within a particular cycle. Okay, any questions about this? So I'm going to talk a little bit about, on the operational side, this idea of battery degradation and the way it relates to sort of different operational aspects of the battery. So, how does battery degradation relate to kind of the use of your battery depending on the state of charge? The rate at which the battery degrades or loses its overall capacity can depend on a whole lot of factors. And we're going to be looking on this slide specifically at how it relates to changes in your state of charge. So if I have a larger depth of discharge, that means it's going to be a faster degradation. And so you can look here, for example, at the black line compared to, let's say, the blue line. Okay, and so The black line, I'm drawing that out on my arrow over here. That's the very bottom line compared to this blue line. So on the x-axis is the number of cycles. So I'm sort of using the battery and then charging it back up a bunch of times. If we look at, let's say, around 4,000 cycles, we can see that in the black line, you've degraded maybe some 80%, or you've degraded about 20% of your full capacity, whereas the blue line has only degraded about 15%, right? So it still has 85% of its capacity left. And so the difference between these two lines is that when I'm cycling the battery, the black line is doing a 50% cycle, so discharging half of the battery and then charging up, whereas the blue line is using 25% of the capacity. So it goes from, the black line is 75% of the capacity. It goes from 100 to 25%, and the blue line is doing 100% to 50%. So the black line is doing a larger depth of discharge, and it is then decreasing in the total capacity of the battery faster over the same number of cycles. We'll also notice that in terms of the trends, right, the more cycles that you're doing, the more you're degrading. So the more you use your battery, the more it'll degrade. And then the other thing is the sort of starting point of your depth of discharge and kind of your operating range can change as well. So let's look at an example of two things where you're doing the same amount of depth of discharge, but you're starting at different points. So let's compare the green line to the red line. So the green line degrades less than the red line. They are both discharging a depth of discharge of 60% of the capacity, but the red line is going from 100 to 40, and the green line is going from 85 to 25. So they both discharge 60%, but the green one doesn't go above 85%. And so remember what I was saying, the more you're operating at like higher levels, then kind of the more you're stressing out the battery. And generally, the like closer you are to like the 50%, the better it is for the battery. And so the 85 to 25 is operating in, let's say, a more sort of comfortable operating region of the battery, and so it tends to degrade less, whereas charging it all the way up to 100% will accelerate the degradation in comparison. Okay, any questions about that? So when it comes to like the use of the batteries in your like sort of common consumer electronics, I would just kind of caveat that like a lot of this stuff is fairly well known, and the battery management systems are kind of well designed, and we have buffers in there. And so the amount of degradation, like if you were to charge your phone to 90% every day to try and preserve some of the battery, that definitely works and it definitely helps, but the the relative difference in degradation is not going to be as large because they build in the buffers and because they have good battery management systems. So I would say don't feel obligated to necessarily, do optimize like the charging of your consumer electronics on your own. So what other aspects of what other aspects of operation are related to degradation? Another big one is temperature. Okay, and so battery degradation can also accelerate at sort of extreme temperatures. So typically, if you're operating at really high temperatures or really low temperatures, you can have higher degradation. So this particular plot, they're looking at the number of cycles So the cycles are actually by the different colors. So as you go from top to bottom, you're going from 1 cycle to 50 cycles to 100 cycles to all the way to 250 cycles. And you can see that as I go from top to bottom, the amount that's actually degrading increases at sort of higher temperatures. And the last one that I'll talk about is with charging speed. Okay, so the faster that you charge your battery, the more you're sort of stressing out the battery. So this particular plot is showing the differences in degradation. So this y-axis is essentially the percentage of your like capacity loss in a full cycle if you're charging at different speeds. So the speeds are 1C, 2C, 3C, 4C, all the way up to 6C. And what that refers to, it's kind of like a ratio of the capacity over some given amount of time. And so, 2C is twice as fast as 1C, 3C is 3 times as fast as 1C, and so on. And the trend generally is that the percentage of degradation increases, right, as I charge faster and faster. And there is kind of a difference in effect depending on the temperature that you're doing this in. But generally speaking, right, charging at higher power can accelerate battery degradation. These are just like physical properties of the batteries. There's not really any way to avoid this. But I would say that all of these plots that I'm showing you and these effects that I'm talking about, these are like laboratory results, right? And so a lot of modern day consumer electronics, as I've been saying, have built-in sort of protections to mitigate a lot of these degradations. So they're not going to be as extreme as the types of degradation and the level of degradation that we often see at the lab level. So an example of one of the battery management systems in electric vehicles is how they manage charging speed. And this is actually specifically to deal with some of the issues regarding degradation of batteries. So this is maybe less commonly known for folks who haven't driven and charged electric vehicles and does come as a surprise to some. But it's not really like, when you're charging a car, it's not really like filling a gas tank of gasoline for your gas car, okay? When you are filling up your gas tank, you just put in the gas nozzle, it fills up at a linear rate, right? And it takes some set amount of time, kind of no matter, the amount that dispenses doesn't really change over time. That's not true for charging, especially charging at higher speeds. Because of this issue with charging at higher speeds, particularly when your battery is more full, auto manufacturers have built in sort of charge management systems that will control the speed of charging as the battery fills up more and more. So the plot that you're looking at is a whole bunch of different vehicles where they plug in to a fast charger, and then you can see the rate of charging changes as the battery gets fuller and fuller. So generally speaking, with fast charging, there's usually a big drop off at 80%, where charging generally is going to slow down quite a lot. And that's because your battery's getting essentially fuller. It's, if we're thinking about that water analogy, it's like harder to pressurize the system. And if you charge it at really high speeds, you could actually damage the battery quite a bit. And so at 80%, there's this rough rule of thumb that people talk about, that going from 80% to 100% they've slowed it down so much that it could actually take as much time as it takes to charge from 0 all the way up to 80%. We can see that some vehicle models will sustain the rate of charge all the way up to 80% before dropping. So here's an example of that. Whereas some vehicles will kind of just continually decrease the speed as you get closer and closer to 80%, whereas others have these like step down functions. So it'll charge really fast at the beginning when the battery is really empty. It'll drop down, charge, and then drop down again. So you have these sort of stepwise functions. You'll also notice that vehicles will charge at different speeds. We're going to talk about that a little bit more in a different lecture that focuses more on the charging behavior aspect. But here, just note that all of these decisions that automakers have been making on managing the battery system pretty much all have to do with sort of maintaining the physical properties of the battery and making sure that that they're not accelerating the degradation. And we'll talk from a sort of policy perspective why that was important for manufacturers to do as well later on in the class. Okay, so all of that having been said, kind of what does this look like in the real world? So we've actually taken a look at kind of real world data of degradation. And so some of those lab examples you were seeing, oh, the battery is degrading, 10, 20, 30, 40% over time. This is kind of what it's looked like for a bunch of Teslas that we looked at. So, driving on the order of 150,000 kilometers or about 100,000 miles, a lot of them are losing, about 5%, a little more than 5% of their capacity. Okay, so a lot of battery experts, a lot of folks in the EV space for a long time were kind of curious about what that degradation would look like once we're thinking about the use of these batteries in the real world. And a lot of folks predicted that it would be actually quite a lot worse. And for maybe the earliest generation of electric vehicles, that was true. But for a lot of what we see now, the battery management systems are so robust and automakers are so conservative with adding buffers on the capacity of the battery that the degradation has not been kind of as bad as a lot of folks have worried about. Okay? Any questions about that? Okay, so keeping all of this in mind, quick kind of discussion question. Thinking about all of these things, if you owned an electric vehicle and you kind of wanted to maximize the battery life, what behaviors might you change? So I know that there's some tables with just one person. Maybe if you want to hop over at least temporarily and talk with other folks, have a quick discussion, and then we'll reconvene and talk about what strategies that people take. All right, let's reconvene, and I'd love to hear some strategies from around the room. Anyone want to volunteer? How about table over there, you guys?
What we said is to make sure we don't charge to set the charger capacity at, for example, 80%, um, and then to also make sure we end the trip before the battery drops below 20%, to
Yep.
make sure it's kind of like in that healthy range.
Yeah, so that's actually that is a common thing for a lot of electric vehicle owners that they will charge to like 80% or 90%. In fact, a lot of the manuals will actually tell you to do that unless you're like making a long trip and then you can charge it all the way up. And so that is a pretty common thing that folks do. Yeah, that's a good one. Anyone else? Any other ideas? How about over here? You guys discuss anything like that?
I mean, you mentioned to not charge last minute as one of the ways to help, because if you do it last minute, you want to do like fast charging, and that's like an easy way to make the battery faster.
Yeah, exactly. And so avoiding trying to fast charge too much. That was actually a really big one that a lot of folks wondered about. Yeah, slamming a lot of electricity into your vehicle at a high power, we would assume would kind of degrade it faster. Oh, and principally speaking, it should. Although it is kind of interesting, looking at this particular data set, I will say that it was pretty difficult to find like a correlation between the speeds that people were charging and whether it was degrading faster. And so that really does speak again to the good sort of battery management systems. That surprisingly, uh, yeah, folks who were only like going to supercharger stations, we were finding that their batteries were not necessarily degrading any faster. But still, I mean, I would be hesitant to really sort of generalize that without digging into it more. I think in general, it's probably a good idea not to just fast charge all the time. Okay, good. And I think those are kind of the two main ones. And there are a lot of other like minor things that you could do. But generally speaking, keeping your battery, not sort of topped up all the time, and then kind of reducing the use of fast charging will help maximize your battery life.
What about temperature?
Yeah, temperature, although I guess you would have slightly less control of that. So operating your car in really hot temperatures or really cold temperatures, obviously it would be more ideal if you were in more moderate, like actually the vehicle actually tends to like slightly hotter. So in the like 80 to 90 degree ambient temperature range is better. Once you're at like over 100, or if you're operating below, let's say, even 50 degrees, 40 degrees Fahrenheit, you will see that the battery operation is degraded a little bit and the degradation does accelerate. The only reason why I'm saying, in terms of this particular question, it could be unavoidable, right? If I lived in a cold climate, uh, I don't know if I'd be able to avoid, using the car when I need to, when it's cold out. So, yes.
If you had it in the garage.
Yeah. So, okay.
Outside,
Yes.
you could charge it better in the garage if it's cold.
Yeah, that is true.
If
That.
it was 117 degrees, you could put it in the air conditioned garage.
Yeah. Yeah, that's fair. If you have access to like a temperature moderated garage, then yes, that would help certainly. Any other questions or comments? Yeah.
When you said the high or low, like extreme temperatures are bad for the battery, is that just when the car is running or when it's charging or like all the time?
So kind of all the time, but when it's operating, the effect is going to be maybe a little bit more pronounced. Yeah, because you're actively sort of charging or discharging the battery. And so doing that at temperature extremes is going to be worse. Yeah. Great. Any other questions? Okay, so let's talk about the sort of chemical properties of batteries. And before I get into kind of specifics, one thing to keep in mind is that there are many different battery chemistries that have lots of different purposes. And those are balancing a lot of different sort of attributes, right? And so this particular graph is showing this, often there's this trade-off between energy density and power density. And so just to clarify and be very specific about what I mean there, so energy density is kind of how much energy the battery can store. So you can think about this as like more energy density means you have a longer range car. Whereas power density is about how much electricity the battery can output in a given time, right? And so power density might mean, oh, with a particular power density, I can drive like a small car, but I would need to increase the power density to be able to drive like a truck, right? Because you need more power to move that larger mass and larger vehicle. And so, you know, it may be harder to actually do these larger format vehicles and still have a larger range because oftentimes the properties of the battery chemistries are making trade-offs between energy and power. And so this is what's being shown in this particular plot where you have a couple different examples of chemistries and kind of the range of powers and energy that they're kind of encompassing. And note that it's not all just about energy and power, right? There's other attributes that we care about, such as the economics, right? The cost of it. And so, you know, maybe for, you know, like a small consumer electronics, you know, an alkaline battery, which there's kind of this reference point here, right? It's very cheap, not very energy dense, but you don't need it to be, right? And you prefer the economics of it as opposed to trying to maximize on energy and power. Whereas for different use cases, you may favor other sort of battery chemistries. And so that's a lot of what we're going to talk about here as we dive into specifically electric vehicle battery chemistries, what sorts of trade-offs are being made across what sorts of attributes. Yeah, and so the one that's used in electric vehicles are lithium-ion batteries in comparison to some of these other chemistries, right? So lead acid, the big, heavy, bulky ones that are used actually in traditional cars today, and actually you'll find them in electric vehicles as well for sort of antiquated reasons. Then you've got like nickel metal hydride. Those were in a lot of the early generation hybrids. And now we're kind of in the world of lithium ion. And then you can see there's a couple other ones here like lithium phosphate, zinc air, lithium metal. These are much more advanced chemistries that are more in the R&D phase as opposed to sort of commercially available. And we will cover some of those advanced chemistries at the end of the class today. But we're going to be focusing now on lithium-ion batteries. And so a lot of consumer electronics use lithium-ion batteries, right? And so your phones, your laptops that you guys are all using right now are likely powered by lithium-ion batteries. And so I'm sure most of you guys have heard about lithium-ion batteries. but actually that refers to a whole family of chemistries. And so we're going to look at the different, the specific chemistries within the lithium ion family right now. Okay, so lithium cobalt oxide, or LCO batteries. These are very common chemistries, and the application is used in smartphones and tablets and laptops, but are not really used in automotive applications. And the reason for that is these actually have very high specific energy, which means that I can get a lot of use out of them, right, in a single charge, but relatively low power. And so they wouldn't necessarily be able to, turn the wheels of a car and move something with a lot of mass. But to do something like power your phone or your laptop is perfectly fine. These actually are going to be relatively more expensive because of certain materials, so specifically cobalt, which we'll talk a little bit more in a bit. Relatively speaking, compared to some of the other batteries that we're going to look at, these have low thermal stability and kind of short life cycles, right? And so if the battery in your phone is getting really hot, right, it's actually going to degrade much faster. It's less stable and more sensitive to kind of the relative temperatures. And then the life cycles, the number of cycles that we can do for that battery compared to some of the other lithium ion batteries is going to be relatively lower. And so if you're cycling like your vehicle compared to your phone the same number of times every day for years on years, right, how long before your phone battery is unusable? Maybe 2, 3, 4 years. How long before your car battery is unusable? That's going to be a much longer time frame, right? 15, 20 years. And so in terms of like relative number of life cycles, LCOs are going to be a little bit worse. Okay, the next one we'll talk about is lithium manganese oxide. These are lithium batteries that don't include cobalt. And so this is going to be a common theme as we move through the families of lithium ion batteries. Whether or not they use cobalt actually has a lot of interesting repercussions. On the operation and performance side of things, the cobalt means that you can actually, you actually tend to have a little bit lower energy density, but these will be thermally a little bit more stable. They charge quickly, have high specific power, but again, as I mentioned, lower energy density and relatively low cycle life. So the very first generation of Nissan Leafs used lithium manganese oxide batteries. There is some kind of developments in this area where they're like trying to add nickel. So this is a different variant of LMO, and I think there's some companies that are kind of exploring this for commercialization, but generally speaking, LMOs are not really broadly used in electric vehicles anymore. Another fairly rare one is lithium titanium oxide. So almost all lithium batteries have carbon anodes, and this particular chemistry uses titanium nanocrystals instead. And it's a sort of interesting concept, but tends to be a little bit more expensive. They can recharge faster. They have high power with long life cycles, but still relatively low specific energy, right? Without that cobalt. The only vehicles that were using this particular chemistry were very small volume manufacturing vehicles. So the Mitsubishi i-MiEV and the Honda Fit EV, both of which did not sell, I would say, a tremendously large number of vehicles, use this particular chemistry. Okay, and now moving on to, I would say, kind of the big three. So NCA batteries, or lithium, nickel, cobalt, aluminum oxide batteries. This is, or I would say was, kind of the flagship battery used by Tesla. Nickel, the inclusion of nickel was used to enhance energy density. These things have pretty good specific power, have a pretty good life cycle, but generally speaking, less stable than other lithium technologies. And so when you do like thermal management of these guys, tends to be, you tend to have a more sort of robust management system. And the materials are fairly expensive. You're using both nickel and cobalt, which both of which are among the more expensive, rare earths that are being used in these batteries. Okay, and so for a long period of time, this was the primary battery format for Teslas, kind of across their offerings. So Model S, Model Y, Model X, and Model 3 all used essentially variations of this NCA. There's since been a transition to a different chemistry, which we'll talk about in just a moment. So if you're not Tesla, the big one that I would say most other automakers were using was nickel, manganese, cobalt. So instead of aluminum, you've got manganese in there, and this has slightly different properties. So high energy density, longer life cycle. The nickel is kind of less stable, but combined with manganese helps to kind of get the best of both worlds, where you have a more stable chemistry as well as kind of a high energy. This particular battery chemistry has maybe a little bit lower power, but much more stable than LCO. Yeah, so again, one of the more popular battery formats for most other electric vehicle models. A couple years ago, GM announced that they would have this whole like Ultium battery line, and those were based off of a specific chemistry of the nickel, manganese, cobalt battery. Okay, and so those were two of the three big ones, and I would say the kind of big up-and-comer that many vehicles are transitioning towards is the lithium iron phosphate battery, so LFPs. So iron phosphate, both of these are in general much more available materials than some of the rare earths that we were talking about, right, with cobalt and nickel. And so from an affordability perspective, a lot cheaper. But not only that, right? So we're balancing economics against these other attributes. These tend to have very high cycle life, very good power density, and are considered to be very safe. And so actually some of those lab experiments that I was showing at the beginning of class, when you do that to these LFPs, they like barely degrade. And so the use of LFPs has been really touted as like, these are the types of batteries that like, oh, you could be fast charging your car all the time and you would basically see no degradation. You could be charging your battery up a lot fuller and see much less degradation. And so this, from a cycle life and stability perspective, LFPs are quite good. The one area where they're maybe lacking a little bit more is on the energy density. And so you got to pack more LFPs to like get the same amount of range in your vehicles. So there is that sort of trade-off. At this point, I would say most of the Model 3s and Model Ys from Tesla, right, that's their sort of largest volume selling vehicles, have kind of shifted over to LFP. And a number of manufacturers are also kind of switching to this chemistry. I'm kind of not as familiar with the situation in China, but my understanding is that a lot of the manufacturers, the main chemistry is in LFP technology. So I would actually really expect LFP to kind of continue to grow, and that the other two, so NCA and NMC, the two big ones that others are using, will probably shrink over time. Okay. Actually, before I jump to this, any questions about any of these chemistries? Anything folks are wondering about? Yeah, it can make the kind of shopping experience a little bit weird if you care about this kind of stuff. Finding information on like what specific model has a specific battery can be a little bit challenging, and I guarantee you that no one at the dealership is going to be able to tell you. But from a consumer perspective, maybe some of this stuff really isn't that important, right? It's like, I want a car that's able to work. I don't want to like necessarily think about these things. And so really it's on the job of the auto manufacturer to make sure that at the end of the day, whatever battery we're talking about can satisfy the requirements of the consumer. And so, they are doing internal optimizations for what the right chemistry is to use. But if we care about these details, right, there are some pretty interesting trends that are happening with battery chemistries, and I think LFP in particular has been one of the more promising chemistries lately. All right, so talking about the sort of trade-offs, this is kind of the type of diagram that helps display some of those trade-offs. And so there's a bunch of different attributes, right, that we care about with our battery. So what's the energy density? What's the power density? How safe is it? How well does it perform? What's the lifespan and how much it costs, right? And so different batteries are kind of better at certain things and worse at others. And so this is kind of a diagram that shows that visually. Oh, yes?
What do you mean by safety here?
Safety is like how stable the battery is. Like, so if it is subject to certain like stresses, like thermal stress, right? Is it gonna degrade faster? Is it more likely to have catastrophic failure? Those types of things. So there are like diagrams like these that you can find all over the place. And the only sort of caveat that I'll say is that like some of these can change over time. The way that people think about certain attributes is different. And so this is like a different one that I found that looks at a certain subset of lithium-ion chemistries. In general, I think they're gonna align pretty well, but just know that there are some nuances depending on the way people define some of these attributes. I have like a couple slides here that I just put in for reference, right? Because you guys have access to the slides. I'm not gonna like go through this. This is, these are tables that tell us like what battery chemistries are in what vehicles. And this changes all the time, right? It gets updated and new vehicles come out. But if you're like interested in understanding what chemistry goes with what car, I'm just adding these slides as kind of references. There's one last sort of nuance that I'll talk about with chemistries that I haven't mentioned yet. You'll notice that in this table, it's got NMC 721, so nickel, manganese, cobalt. And actually within that, there are different ways of arranging the chemistry in the battery, and you can actually have different proportions of those materials, which is what these numbers refer to. So when I see NMC 721, that's saying 7 parts. So this particular lithium-ion battery chemistry has 7 parts nickel to 2 parts manganese to 1 part cobalt, versus 622, which is 6 parts nickel, 2 part cobalt, 2 part manganese. That's what these numbers are referring to in these tables. Okay. Okay, and so just to give a sort of view of what that has looked like over time, as I was kind of mentioning, right? So in 2017, the vehicles that were sold, some of them were NCA, some of them were NMC, and NMC of different types, so 333, 532, 721, and then some of them are LFP. And the trend that you'll see is that LFP, after its sort of introduction, has started to grow more and more. The really popular one from 10 years ago, which is the 532 and 622 NMC batteries, those are starting to decrease in share. And so there are these trends and shifts in the chemistry of batteries within vehicles over time. That's all on the cathode side. On the anode side, like I mentioned, it's mainly graphite, and that hasn't changed a huge amount over time. There are these variations of graphite where you combine it with silicon, and those are starting to increase in popularity, but generally speaking, I think those are kind of just variations of graphite anyways. Okay, any questions about that? All right, so let's talk about battery safety. So maybe this will get a little bit more specific on the question earlier. I'm sure that folks have seen in the media these articles about how like electric fires are kind of going up in flames. So this is there was actually a video of this one, kind of interesting. And so this was after a hurricane. I think this one was in Florida, where the garage flooded. And so remember, so kind of what's happening here, you've got these really high energy and power dense batteries that have a lot of electrical potential, and you flood them in with seawater, right? Which is going to allow for those batteries, if it gets inside of the battery, it's basically going to short circuit the battery. You're allowing the electrons to, and ions to kind of freely flow to where they want. That increases the temperature extremely quickly, right? So think about all of the energy that would be required to move a 4,000-pound vehicle 300 miles. All of that energy is getting released at once. You have a huge increase in temperature that leads to these battery fires. So that's like one example of how this might happen, right? So causes of these battery fires. So internal short circuits, so damage to the physical separators between the anode and cathode, sort of allowing, I apparently didn't finish this bullet. It allows for sort of a direct release of your ions to go where they want in terms of releasing that potential energy. So we typically think about these things as thermal runaways. So there's a chain reaction where an excessive amount of heat causes further heat release. So this is this kind of phenomenon that even if you were to damage like one small portion of the battery, if you were to cause that particular cell to heat up and then release a bunch of heat, it could damage cells nearby, leading to this runaway chain reaction. And it can be hot enough to actually ignite the material in the batteries. Right? Mechanical damage. So if you have like an accident or your, improper handling that can compromise the integrity of the battery. Electrical overload, so overcharging, rapid charging beyond its limits can cause excessive heat and then lead to thermal instability and eventually thermal runaway. This one's probably a little bit harder to do on like a battery with a management system. Um, it has sensors that can detect if you are charging too quickly, if the battery's getting too hot, and it will like throttle the amount of charge that the battery can receive. So this one, I would say generally is less likely for EVs. And then manufacturing defects, and we're going to see that this is actually a pretty salient one and has happened before. But flaws during the manufacturing process can, for a variety of reasons, sort of compromise the integrity of the battery. So the kind of most salient example of this, I don't know if folks saw this in the news, but GM had a big battery recall. So several GM Bolts, which are full electric vehicles, just kind of caught fire under normal usage. So these are vehicles that were not involved in a crash in any way. Sometimes they would just catch on fire inside of someone's garage when even no one was using the vehicle. And so Bolt EVs that were produced between 2017 and 2022 were recalled, so over 140,000 vehicles. And they did find out later on that there were battery modules that were defective. So we're going to look at the form factor of batteries in just a second. But essentially what happened was the way that these battery modules were kind of put together, or actually the cells themselves were put together, there are these tabs that form part of the anode that are kind of folded over. There's a separator there that makes sure that it's kept physically separate from the cathode, and the stamping process to do this was not happening correctly. And so you'd have these defective battery modules that could kind of spontaneously leak electrolyte and lead to thermal runaway events. So that actually wasn't the fault of GM. It was the fault of the battery manufacturer who provided the cells and modules to General Motors. And so LG was their supplier, and they actually ended up agreeing to reimburse General Motors for all of the costs related to the recall. And that was a particularly expensive recall, right? Recalls are, in general, a pretty expensive proposition. Battery fires are particularly challenging. Now EVs are kind of widespread enough that there are kind of well-developed protocols for a lot of firefighting units to be able to handle this, and they do have like pretty specific procedures in the way that they fight battery fires. So you have to use PPE, you have to use these like suppression blankets, and you have to, after you put the fire out, you have to continue monitoring the battery for some amount of time because it can actually reignite if the thermal runaway kind of continues to happen. So these are self-sustained chemical reactions that can last for many, many hours, and they can reignite later on. And as I mentioned before, because these are specific chemical fires, they can actually, a lot of these fires can happen even in the absence of oxygen. And so, you could suppress all of the air around it, which would put out most normal fires, but these could kind of continue to happen. Yeah. Any questions about any of this? Yeah. Suppression blankets, those help to kind of isolate the fires. And in the cases where it is one that is, you can get rid of the secondary fire effects. So like, even if it's not like oxidation combustion, if it gets hot enough and you have a fire and it's starting to cause other parts of the car to undergo normal combustion, you can choke that out with these suppression blankets. Yeah. Anything else? Okay. Yeah, and so these incidents have led to a lot of really big backlash. I think one of the more sort of notable ones is in South Korea. There were a couple of like really prominent fires that happened in these like big garages, and so there was like this big public backlash against EVs. They ended up like banning electric vehicles from underground parking for some period of time. A lot of chargers ended up getting removed. There were like limits on the way that you charged the vehicles. And kind of since this series of events that happened a couple years ago, Hyundai, which is like one of the big Korean manufacturers, and the Korean government have actually led this like big international working group to improve battery safety, both on the charging side and on the vehicle side. Okay, and so we've talked a lot about sort of EV fires in general, and I want to maybe back out and talk about kind of in the bigger picture. Well, I guess, so raise your hand if you've heard about like EV fires in the news, just in general. Yeah, so a decent number of folks, right? And, for one reason or other, media has tend to kind of focus on them. But if we look at the actual sort of data, gas car fires, so conventional vehicles catch on fire as well, and at a rate much higher than electric vehicles. Right, so gas cars are involved in fires at a rate of about 1,500 fires per every 100,000 cars, whereas EVs are maybe at about 25 fires for 100,000 cars. And so that ratio is like, for all of these fires that you see here, that would be one EV on fire. That isn't to necessarily kind of discount the severity and the importance of addressing this as a safety issue. Right, there are differences between gas fires and electrical fires. Gas cars, all of the fires with gas cars are almost basically always while that vehicle is operating, right? These are like old vehicles that are not maintained well, the engine overheats and you have fires or some other sort of incident like that. EVs have like caught on fire just like spontaneously without anyone operating the vehicle, right? So it could catch fire in the garage. And so, yeah, the format of the fire is a little bit different, and that is important to consider. But kind of at the end of the day, just know that despite what you may hear in the media, from a sort of purely analytical perspective, we know that gas cars happen with a much higher frequency, right? Order of magnitudes higher frequency than electric vehicles. Yeah, and so kind of quick discussion question. So if it's the case that electric vehicles catch fire much less often than gas cars, I guess I have a question to pose to you guys. Like, why do you think that people often perceive them as more dangerous? And maybe I don't necessarily have the answer to this question, but I'd am interested in hearing your guys' perspective. So take a quick moment to have a discussion, and then we'll hear from you guys what you guys think. Okay, let's reconvene and have a quick, maybe around the room, see what people are saying. What about you guys? Well,
So we had two things. One was regarding like the nature of the fires, battery fires being much more difficult to put out than
okay,
gas.
the fires are more severe.
And then the perception of them being more like that EVs are now more widespread, and more in the view of normal people now,
Uh-huh.
or just regular everyday people now. And on top of that, a lot of negative news, it catches people's attention more than positive news or anything of that sort. So this new technology having all these mistakes or this huge event that's happened, it's easier to have people see that and be like, oh my god, versus gas fires have fires, okay.
Yeah. So it's like a new thing. We're so used to seeing gas fires, people maybe don't care about it. But with EVs, yeah, maybe the fact that it's a new technology, it's interesting to highlight. Yeah.
I think people maybe attribute gas fires to human error more so than they do with EVs. Because you see these videos on the news, EVs getting into the garage, for instance, parking, and just randomly catching on fire.
Yeah. Whereas a gas car, it's like, oh, it's because they didn't maintain the car well or something like that. Yeah, okay. Anyone else? Did you guys have anything different?
I think the one thing you said was that the thought of it catching fire when you're not there is scarier.
Yeah.
If you're there, then at least you can call the fire department or something.
Yep.
If you're not there, it can be a lot worse.
Yeah, exactly. So, if I leave my car in my garage and I go out on vacation and I come home and the house is burned down, that's less likely to happen with a gas car, certainly. Yes. Yeah. So the type of fire is just more difficult to deal with. And so, yeah, maybe that makes people kind of latch on to that a lot more. Yeah.
Speaking as a new tech mechanic, we're a lot more concerned about the electric because like in the buses, the batteries make up a very large part of the bus.
Uh-huh.
So if something were to go wrong, number one, we're not as familiar with them as we are like the CNGs for so long. And part of it as well is that if something were to go wrong, it wouldn't develop a large portion of the bus because of the CFUs, which is just the engine is just the back of the bus.
Okay.
That can contain something that goes wrong at the back of the bus. But for the electrics, the battery runs around the bottom of the bus, and we do know that they are faulty to an extent because they have all been recalled.
Yeah. So specifically the batteries in the Unitrans buses have been recalled?
Yeah, to require the battery plant nearby, I think there was one like somewhere in Northtown got shut down and some problem got going on.
Ah,
So
okay.
they've been having like charging issues, they don't charge all the way, or some of them don't charge at all.
Yeah.
And
So are they gonna replace the batteries or what's happening with
they're under
those?
warranty by New Flyer, which is where they make it, so there's no one dealing with it right now.
Okay.
But we have in-depth in service, so we have to juggle them throughout the day. Like, we can't run and master run the entire day. We have to pull them back halfway through.
Yeah. Yeah, so, as far as the safety goes, with in particular examples, that can affect, I guess the sort of operational safety is very different between a battery and the CNG, which is the alternative fuel that's used for these buses. So great. I think you guys really kind of hit the nail on the head. There's differences in the perception. Some the extent to which we think about or perceive the risk and how much that risk actually sort of materializes. I think that difference is pretty interesting. But yeah, I feel like in general, gas car fires are not so much talked about in kind of the same way. So, okay, so moving on. So the next piece to talk about is battery production. So how do we actually build these batteries? We're not really going to get into kind of the nitty gritty of the full sort of manufacturing process, but this maybe at least gives some kind of scope so that we can see in general what that process looks like. So there's a lot of steps, right? So you've got slurry preparation, the coating and dyeing, calendaring. That's all preparation of your cathodes and anodes, cutting the electrodes and then putting it all together into your cells. And so that step is kind of the first fundamental piece of the battery, the cell assembly, and then filling it with electrolyte and forming them into modules. So you can see there's quite a few steps in the sort of manufacturing process. And generally speaking, when lithium ion batteries were first becoming more commercially available, they're actually very expensive. There are many areas for cost reduction, everywhere from kind of just learning how to do it better, but then also upsizing the manufacturing process so you get economies of scale. All of these steps are sort of potential areas for helping to reduce costs. So the more batteries that you're producing, these manufacturers are getting more revenue. They're able to obtain better equipment. They learn better production techniques and innovations kind of in the process line. And that's to say nothing of, all of the cost issues associated with the supply chain of the raw materials that you need. So many areas for kind of potentially reducing cost here. That's kind of the main point of this slide. So when that manufacturer produces the battery, really kind of what we're talking about are essentially these cells, right? And so batteries themselves are comprised of different subdivisions, the smallest one being the cell itself. Then you can have many cells as part of a module, and then you have many modules as part of a pack. And so if you have 10 cells in a module and then you have 10 modules in a pack, just know that those costs don't necessarily scale linearly. And so the cost of a module may be more than 10 times the cost of the cell, even though it's like 10 to 1, because you may have other components that will increase the cost, right? And so you need the sort of casing to hold everything together. There are components that will sort of connect the cells together, and then when we start to scale up from 10 modules in a pack, right, that pack again is not going to be 10 times the cost of the module. It could be even more than that, because that's where you're doing additional controls, like battery management controls. You could have like temperature sensors and regulators. All of these things are leading to like incrementally more costs that make it more expensive than this sort of linear scaling just based on the number of cells. The cells themselves have different form factors. And so the three main ones that we'll talk about are cylindrical, prismatic, and pouch. And so you can look at the kind of physical sort of structure of each of these form factors. Cylindrical, maybe these ones are ones that you guys are familiar with, right? If you have like AA or AAA batteries, that is a cylindrical form factor. They tend to have lower packing density, right? And so for some amount of space, you can only arrange so many of these things because they're round, and so you have to keep them in a particular configuration, and you will have like dead space in between some of the batteries. But they tend to have pretty good mechanical stability and good thermal management. I mean, the thermal management is actually connected to the fact that you have some of this like spacing that allows you to do to add certain thermal management pieces to the battery. And then mechanically stable, you have a round object without like corners, sharp corners, and that really does improve stability. Prismatic cells, so this is the structure kind of right in the middle. You have your layers of electrodes, separators, your anodes, separators, and then cathodes arranged in this kind of roll, and then stacked up into these layers. These tend to have better packing density, right? Because they're actually like rectangular, and so you can fit them right up against one another. But the corners tend to experience a little bit more stress, and so if you physically impact these in certain ways and damage the corners, that can lead to thermal instability and thermal runaway events. And then last one, pouch cells. These are cells that don't actually have a rigid enclosure. They're kind of, they're not, the electrodes themselves are in a flexible case. And so there are separate problems with this, especially if they get hot, actually they can swell up, which leads to sort of bad mechanical stability as well. I don't know if you guys have ever seen like older phones that have pouch cells where they like burst open. That's because of this particular structure. Yeah. Yeah. So the actual volume of the battery can change quite a lot. I've heard about that. Those, as I understand, are kind of more in the laboratory right now, not really in commercial settings. Yeah. It's kind of interesting to think about. Like a lot of the batteries are laid in the bed of the vehicle. Like if the floor of your car like goes up and down as you charge the battery, that would be weird.
Those batteries
Yeah, so very high energy density. Yep. Yeah, so we'll actually look at a couple of the sort of more lab-based batteries, and we'll think about what that may offer in terms of like performance and operation for future vehicles. Right now, we're kind of confined to these ones, and they are still incrementally improving. But yeah, there's some maybe some more revolutionary designs that might be interesting in the future. Yeah, okay, and so that's on the form factors. So what about the battery materials themselves? Where do we source these things as they go into production? Um, this is maybe a little bit more antiquated of a chart. I would say in the last like 2 or 3 years, there's been a big push, right, to open rare earth mines and locate more resources. You know, in the US, for example, they really want to onshore a lot of this. And so there's been, yeah, again, kind of this move to maybe start shifting away from reliance on certain countries for certain materials. So the big ones that you see here are lithium, nickel, cobalt, and graphite. Um, yeah, and so lithium, the really big ones that we talk about are in Chile, Australia, and China, all of whom produce a lot of the sort of raw form of these rare earth materials. Cobalt, famously, the vast majority of cobalt comes from Congo, and we'll talk about the implications of that in just a moment. And then the other big one is graphite. Yeah, so graphite, as we know, is important for the anode material. The big ones, so actually, you know, this map differs from a little bit of what I have in my head, my understanding. So China is a really big one for graphite, and Mexico, I know, is a big one for graphite. And then there's a couple other countries, you know, that are showing up here. So thinking about material extraction, what are the sort of environmental issues with doing this? So extraction, right now, the most common process is known as brine mining. So this is where you extract lithium from saltwater reserves. The way that they do this is they have these like large pools that cover large amounts of area so that the water can evaporate and that they can deal with more sort of solid materials. And this has pretty severe local environmental impacts. So we're thinking about toxic metal contamination, underground fires, particulate pollution, and it's very energy intensive. The mining itself does result in some like greenhouse gas emissions, so specifically with carbon dioxide, but actually that I would say is kind of lower in the sort of order of magnitude and importance of environmental issues. Like the extraction of regular fossil fuels actually leads to a lot more CO2 emissions than lithium mining. Any questions? All right. So the chart before that I was showing was the map of where we actually get lithium now. But we also have some idea of like where the resources are actually located, you know, whether or not they're actively being extracted. And so there are different forms of lithium that we can use. So continental brine, geothermal and oil field brine, from volcanic sediments, and then from pegmatite and from granite. So different resources are being used in different ways. There's actually a really big resource. I think that's labeled number 12, 11 or 12 here in California. Has anyone ever been to the Salton Sea in like Central California? It smells really bad. Actually, there is supposed to be a pretty high concentration of lithium resources there, and so likely in the near future, we'll see lithium extraction operations actually starting place in California. Any questions? All right. The other one that I would say is kind of on the high end of like environmental issues, but not only environmental, but also sort of labor issues, is in the Democratic Republic of Congo. So they produce the majority of cobalt in the world, and they are sort of hand mined. People estimate between 140 to 200,000 people work as what are known as sort of artisanal miners in the Congo, and there are very serious sort of labor issues. It's dangerous in polluted conditions, and there's violence around like racism, discrimination, and especially worker abuse. And so cobalt has kind of this double whammy of being environmentally harmful locally, as well as sort of a humanitarian issue in itself. Yeah, and so question for you guys. Do you guys think that EVs actually solve environmental problems, or are we just kind of shifting them elsewhere? So I'd like to have you guys think about kind of the implications of what I was just talking about. You know, we think about EVs as, you know, traditionally this green option. It's meant to help the environment, but what does that mean relative to some of these issues that I was just pointing out? So have a quick discussion, and then we'll talk about this together.
I think the issue that with EV,
You're not supposed to. You're not supposed to. You don't have to.
I don't think there's any like one solution, so it doesn't solve it. But I think, especially in a country like America, it's so dependent on cars. We're not going to see like wide scale shift to transit in the near future. So EVs are less large and traditional cars that I think are pretty important. I think the big issue with EVs is how solves your personal car.
Right.
Which is also identified car companies. It's easier to control what you yourself do, but it's more effective to control.
Like there's stuff.
So like it's not a bad thing. It is obviously we're trying to
Like a lot of I know.
you can find a way to make it more
Like revenge.
still just
Okay, let's reconvene here. Okay, what do you guys think? And are these solutions, or are these problems? Any you guys want to talk about your discussion.
Basically, I think it's just shifting the problem is the truth, but then you could really argue that's kind of just always what will happen, I think, because if we're gonna get super philosophical and stuff here, I think it's honestly more just consumerism. I think as long as countries unfortunately will do cheap labor, we will take advantage of that because we need the resources, and so then that becomes a whole issue of the company's gonna be like, well, you certainly want that phone that I just sold to you, how am I gonna get the resource? If we could kind of go to any different industry where we've done those changes, so I think it creates new problems, technically solves old ones, and when you're talking about like the data's so new, we don't necessarily probably know all of the problems that like EVs might create, but it solves maybe some other ones.
Okay. Yeah. So thinking more that it's a kind of a shift. Yes.
I know we could take another example of plastic. In fact, was introduced as a way to be more environmentally friendly on stuff on paper, wood, metal. We're trying to save on those resources, but in the end, look how it got us in terms of environmental pollution.
Sure. Anyone else have different thoughts? Yeah.
I think it does create new problems, but you have to consider like the scale of the problems that it creates versus the scale of the problems that gas-powered vehicles create. So also I think that you were saying with like the new types of batteries don't require cobalt.
Yep.
That maybe we could solve some of the cobalt mining problems by just switching to different batteries.
Yeah. Great. I think both of your points are actually exactly what I kind of wanted to highlight. And so you guys are right that there are these sort of shifts in problems where we're creating new issues, right, with this higher demand for rare earth materials. But if you really want to do an environmental assessment and understand kind of the impacts, you have to understand, what are the costs and what are the benefits, right? And so when we think about in totality, the greenhouse gas mitigation of electric vehicles compared to gas cars, I would argue that the benefits of that would actually swamp a lot of these like local issues that are now happening as a result of EVs, which is not right to dismiss the importance of thinking about these carefully, but if I am achieving $1 billion worth of societal benefits in reducing greenhouse gases, but I'm causing $1 million of damages, right? There's that calculus can lead me to think that this is actually a really good thing, right? And so when you hear about the trade-offs and drawbacks of certain technology solutions, you want to be thinking about the sort of real assessment of impacts, and that means you actually have to like understand the sort of quantification of what's happening. Yeah, and so I would generally argue that the environmental benefits outweigh the harms that are being caused. But the other point is, we do see there are new problems being caused by EVs, and so in what ways can we mitigate that? And so kind of exactly as you were pointing out, one of the big things is like that cobalt issue, the humanitarian piece of it, that's been known for quite a while, and actually a lot of automakers actually made a concerted effort to think about ways in which we could either, one, reduce the amount of cobalt, right? And so think about chemistries that use proportionally much less cobalt, or even chemistries that don't use, some of these rare earth elements. And so that shift towards LFP, I can certainly say was at least in part influenced by the drawbacks of having to mine these rare earth elements. So there are these issues that are happening, and we can't dismiss them. but we have to sort of contextualize them in terms of, the trade-offs that are being made, as well as thinking about ways in which we can progressively, solve those issues. Okay, great. So let's run through the last bit here. So most of what I've been talking about with kind of the materials has actually been focused on the mining and extraction, right? So thinking about where those materials are located worldwide, and then who is getting that stuff out of the ground or out of the water. But importantly, in terms of the like production process from the raw material to the battery, that is only one phase. There's three main stages, right? So the mining, which we just talked about, and then there's the refining of the material, because you have to get that material into a form that can actually be used in the battery, and then manufacturing, which is like putting together the battery itself. And so whereas mining, we've seen kind of, depending on the material, it's getting extracted in different countries all around the world. The refining part of it, if you look at this, the sort of portion that one particular country is responsible for is sort of dominated by China. And so whether the lithium starts in Chile or in Australia and ends up in the US or in Europe, it's a very large proportion of those raw materials are first going to China to get refined. And so that is kind of this step and reliance process, that from a political standpoint, folks are trying to change. And so there's been a step up in thinking about trying to increase refining capacity in other countries. But until that happens, China may be responsible for something like 80% of the battery materials that kind of flow ultimately into the batteries that we need for EVs. And likewise, a lot of that manufacturing is happening in China as well. So that's kind of the phases leading up to the construction of the battery. And there's also this piece kind of at the end. We're not going to actually talk about this too much in the course, but I'm kind of representing a lot in one slide, because the end of life of batteries, there's kind of a lot to think about here. There's this idea of circularity, which is thinking about not only recycling the batteries, but also reusing them. So we think about the use of batteries in these vehicles. They have pretty stringent performance requirements. But once you maybe think about using them in other formats, like the common one is using them on the electricity grid, now you're not having to move things around. You can combine a lot more batteries together. They can be stationary. The performance doesn't necessarily have to be as robust. And so maybe you could reuse them for a much longer period of time. So what I would say about this idea of end of life of batteries and the people who study this, right now there's not so much recycling that's happening, right? The first EVs were coming out in 2010, 2011. How long do cars last? We'll say 10, 15 years. And so back then, very small volume of vehicles, right? Now it's, once we get to the 2016, 2017, 2018, you're starting to see much more vehicles being sold. And so 10 to 15 years later from then, you're going to be talking about millions and millions of these battery packs that are just reaching their end of life on the vehicle side and retiring. And so this is quite a big deal to figure out. Right now, we don't have much recycling. We don't have much reuse. But it's a big economic opportunity, and people are going to figure out business opportunities for these in the years to come. There's still a lot of technological and economic challenges of doing these things. It's still really expensive to do. But I think that's going to change, yeah, in the next like 5 to 10 years. Okay, this is kind of like a duplicative slide. I'm gonna skip this. Battery production. So in the last phase, we're actually putting the modules together into these packs, right? That is happening at these like gigafactories, right? So as electric vehicles become more popular, you got to ramp up the production by quite a lot. And so a lot of these large-scale gigafactories have been popping up all over the world. There's a ton of them in China, and there are quite a few in the US, right? There are lots of different companies with gigafactories that are producing, cells, modules, packs, whether that's for EVs or for other applications. This is an area that has grown quite a bit in the last 10 years and will continue to grow. This is actually a little bit of an older slide, but it's kind of showing how many have kind of opened even just in the last couple of years. Okay, last bit I'm going to talk about with the economics. This is kind of a neat little slide that I like to show. So back in 2014, there was this scientific paper published in the Nature journal, which is like a very high-end, prestigious journal. And what the authors of this study did is they went around and they talked to a bunch of experts, battery experts. So that's like people in the industry, people from like national labs, people who've been kind of working in this area for a long period of time. And they basically said, okay, can you like predict what battery prices will look like over the next like 10, 15 years, right? And so everything that's like shaded to the right, or sorry, to the left, that's all like actual data of like costs of batteries. And so we're talking on the order of like between, $300 up to like $1,300 per kilowatt hour. So so you'll get used to some of the numbers here in just a second, but generally speaking, that's like quite expensive. This red bar here, that line horizontally intersects at about $150 per kilowatt hour. And that's kind of like the golden number that you would get to in order to have electric cars cost as much as gas cars over the lifetime of the vehicle, right? So electricity is cheaper than gas. And so at $150 per kilowatt hour, when you buy a new EV, it'll be more expensive than the gas car. But over the lifetime of the car, you will save enough money from the electricity that you would actually end up breaking even. So 150 was a really important number for the industry to think about, because that's when, at least from the life cycle of the vehicle, you could break even with a gas car. And no one predicted, if you look at all these yellow dots here, all of these experts were making these predictions, and there's a pretty wide band. No one predicted that we would reach $150 per kilowatt hour up until like 2030. But actually, in reality, that price point was already reached. And so, yeah, even the experts, right, they're not able to predict everything. So now no one really talks about the $150 anymore. Nowadays, we focus on the new kind of standard, which is $85 per kilowatt hour, and that's where folks have done the math to estimate that's about what you would need for an EV to break even with the gas car at the point of purchase. So when you go to the dealership and you buy it, it'll be kind of the same price as a gas car once you're at about $85 a kilowatt hour. Okay, and so this is the trend that we've seen in the cost of batteries over time. And I think right now, these days, we're at around like $110, $120 per kilowatt hour. Yeah, so that's quick and dirty on the economics. The last thing that I'm going to close out with is to talk about these like new revolutionary battery chemistry technologies. I'm going to go through this maybe a little bit faster so we can make it on time. The main takeaway here isn't to think about the specific chemistries or properties of these batteries. Just that the sort of advancements here are quite substantial, right? You're talking about really, really different energy densities, really different power densities, but they face really hard difficulties. And the one consistent thing is you're at really high energy densities, and so if anything messes up in the battery, it's very catastrophic failures. And so that's the main challenge that we see across all of these futuristic battery chemistries. Lithium metal anode. So this actually refers to the anode, not the cathode material, and they actually use lithium metal. And the energy density of these things, if we look at the old chart over here, it's much higher. And so you're talking about if I have, an equivalent size of these things inside my car, I could be driving 1,000 miles on a charge or 2,000 miles on a charge as opposed to 300 miles, right? But they have these they end up forming these dendrites, these crystal structures that can penetrate through the electrolyte. And if that penetrates the electrolyte and makes contact with the cathode, you get, boom, explosions, right, and fires. So not good. Lithium sulfur, also very high specific energy. You use sulfur instead of cobalt, much more available material, much cheaper. You're not going to have these humanitarian concerns. This one has the volume expansion that we were mentioning earlier. And there's leakage issues that haven't been really dealt with. Solid states, much higher energy densities, again, 2.5 times higher than existing chemistries. This has a similar issue with the sort of dendrites forming, and so you have lots of fires, lots of explosions that happen with these chemistries. Last one that I'll talk about, lithium air. This actually uses oxygen from the air to help do reduction at the cathode. These can actually have energy density as high as gasoline, which is frankly a totally revolutionary thing if you could get this to work. But again, this is still kind of in the lab phase. The costs are too high, and there's still some technical issues with getting this to work. So there are hybrid cell batteries now where we're thinking about combining different chemistries. That's another sort of future area of potential. I wouldn't call that really revolutionary, but the combinations may help to, detract from some of the downsides of certain chemistries. Okay, and so that's it. There's this kind of future potential to improve these batteries, and so we'll kind of see what holds in the future.